So I think everyone is here, and should I start?
Yes, let me say a few words. Okay, guys, not everybody is here, but we will start. If you know, Abi joined our group in Opran 2 years ago, 1.5 years ago, and he is leading the research in our team. Abi is getting into the coherent area and provide simulation, nonlinear, and other support from the theoretical side. We have here, Abi, people from our group, of course, but also from engineering and people from RDS. I don't think they joined yet, but they will come. So not all of them are expert in optics. Again, if you have, if the pace is too high for you, we will try to do it offline because we don't want to hold all the team. So I hope you will catch up, but we must finish it by 3 sessions. This is 1 session of the 3. So okay, let's start, Abi.
Okay, thank you, Amir. So hello everyone. I hope you can see my presentation from there.
Yeah.
And if you have any problem, you can tell me. So I'm Avi. I think only few of you know me, I guess, in my group. So I'm going to start a training course today, which is on coherent communication. And this course consists of the 3 sessions. So the 3 sessions, the first session will be on the background of coherent communication, is include the transmitter and receivers. The second session will be on digital signal processing, which will discuss about the signal processing at both transmitter and receiver side. And then in the third session, we'll discuss about the recent modulation techniques, which is used for extremely high data rates. So to start with the first session today, we'll start with the background. So we'll discuss about the various terminology, the meaning of higher order modulation, symbol rates, and etc. And then we'll discuss about various ways to transmit and receive the signals as well. So this training course, we designed it for just to give you a taste of flavor of the coherent communication. It doesn't have a very deep discussion or a very analytical, modeling and etc. So if you have, I hope a few of you at least know it, and if you have any problem, feel free to ask. I will be happy to take questions at the end of presentation. But if you have any problem which you are not able to understand in the slides or something, please feel free to ask it. So this is the content of today's presentation. Today we are going to discuss about introducing why we need coherent communication, and then we are going to discuss about the various modulation formats and what is the meaning of higher order modulation, why we need it. Then we discuss about how we can generate these modulation formats using optical modulators. And there are various optical modulators like phase modulator, MZM, like Mach Zehnder modulator, and IQ modulators. We'll discuss about details, why they are needed and how you can use it. The optical transmitter part, we'll discuss about how we use these modulators to generate the various higher level modulation formats like PSK or QAM. Then at the end, we'll discuss about the receivers, and we'll discuss about why there is two kind of receivers, why coherent receiver is needed, and why it's called coherent communication. So we start with the introduction, why we need coherent communication. To understand why we need coherent communication, let's look back what we look at what is happening in the internet in the 1 minute. So in 1 minute right now in 2020, there is almost 1.3 million people logged in, 4.1 million Google search, almost 3/4 million of movies are watched on Netflix, and so on. So it means that there is a huge amount of IP traffic flow through the global IP network in right now in 2020. And this is thankfully supported by our optical fiber network across the globe, which make it possible. But this is the scenario in 2020, and the situation is not finished yet. And every year, the data rate global IP traffic is increasing. This is the prediction by prediction by Cisco, which suggests that by 2022, the global IP traffic will be 400 exabyte per month, which means that a 1 exabyte contains 1 billion of gigabytes. So annually, if you consider in 2022, the global IP traffic will be 4.8 zettabyte, which means uh, that 4.8 to understand how big this traffic would be, the 4.8 zettabyte actually is equivalent to all the movie ever made on the Earth will cross the global IP in less than a minute, exactly in 53 seconds. So this means it would require very huge amount of traffic flow at very high speed. How we can support this huge traffic flow at high speed? The solution is coherent communication. So we need to employ the advanced optical network, which actually employ the coherent communication. Actually, we are already employing it. So so let's know what is coherent communication. And so at the end of this presentation today, we will understand what is coherent communication and how it can support this huge traffic at high data rates. So to start with the coherent communication, understanding the coherent communication, let's understand the current system. The current system we are using, the WDM system. So we all familiar with this WDM system. We use several channels, which is modulated by the data and multiplexed together to transmit over the fiber. The fiber network contain the span of fiber and amplifier. Sometimes it also contain DCF, but mostly the coherent modulation formats eliminate the use of DCF and it's used in the receivers. At the receiver end, we demultiplex this data, demultiplex this optical signal, and extract the individual channels, and then we do optical receiver, like optical demodulation, and to get the data. So this is the usual format user network we use today. However, if you want to increase the global traffic, one way to increase is to increase the number of channel. And unfortunately, the number of channel are fixed, especially in the C band. We may look for the extra band, like we are looking now for L band, but overall, even in the C plus L band, the number of channel would be anyway fixed. So number of channel will be limited, so you cannot increase the traffic very high or the traffic rate at very high speed. So the option is, so when you transmit a channel, instead of transmitting one or two symbols, you transmit multiple symbols. What is the multiple number of symbol per channel? We'll discuss later on. But in increasing the number of channel and the number of symbols per channel, this is called higher order modulation. So higher order modulation means we are going to transmit more and more number of symbols per channel at particular symbol duration. So now our next topic is higher order modulation. So to understand that higher order modulation, first let's dig into what is optical modulation and how we can achieve and why we need higher order modulation. So if you look at the electric field of a laser carrier, that is because in the optical communication we use a laser, modulate it with the data, and so electric field of the laser carrier we can represent as amplitude. AT is amplitude, exponential of its frequency, and the phase. There is additional term in electric field which is called polarization, which is only available with the optical fields. So essentially we can modulate each and every quantity. We can modulate either polarization, amplitude, frequency, and phase, all of it, to transmit the data. So we have basically 4 degrees of freedom, and each of degree of freedom can be used to transmit the data. Now this, as you can see, everything is a function of time. This, I mention it as a function of time because because the laser never give you the constant amplitude or constant phase or constant frequency. Laser has always a small line width, so your omega t is not a single frequency, it has a multiple frequencies. Of course, the line width is small, so not very big one. The phase is vary with time, amplitude is also vary with time. These are called phase noise and the amplitude noise or intensity noise. So this noise is inherent to the sources. So unfortunately, we cannot limit it much. Still, there are various good laser sources actually reduce it to very small level, but the noise is always present from the source of the laser. So if you see that how we can modulate the data, so we can modulate the data in various ways. First one is called amplitude shift keying, which means that we can modulate the data in amplitude of the laser light. It also means that it's also called intensity modulation, because modulating the data means, and amplitude means you are actually going to modulating the optical power or the intensity. So in this case, we can only modulate the intensity or pulse. It's called intensity or pulse modulation because we basically modulate the pulse power of the laser. Next one is frequency shift keying. Actually, we can try to modulate the frequency of the laser, but it's actually very difficult to change the frequency of the laser, and it's required very difficult external modulators. And Fabry parrot cavity is one of the examples to do it, but it's extremely difficult and cannot be possible at high data rates. So usually frequency modulation or frequency shift keying is mostly not used in the optical communication. The next one is we can modulate the phase, and the phase modulation is possible, and in fact it is mostly used and very commonly used in the optical communication. The next one is amplitude quadrature amplitude modulation, means that we modulate both amplitude and phase together, and this actually support very high spectral efficiency or very high data rate, you can say. So it's mostly also in use the QAM, that is quadrature amplitude modulation. The next one we can also modulate is polarization, but polarization is also very difficult to modulate. So basically, we usually don't modulate the polarization, but instead of that, we use it as an extra degree of freedom as a multiplexing tool. So apart from doing the WDM, we actually also do the polarization multiplexing to increase the efficiency by twice. So polarization shift keying is actually used along with the QAM or ASK or PSK, where each polarization is modulated by these three individual format, and then we have two polarization, so our efficiency will increase by 2. So to understand, so these are different modulation format, but how we can represent this modulation format? So constellation diagram is used to graphically represent the modulation format. What is constellation diagram is, you have a modulated signal. We take a real and imaginary part of modulated signal and plot in a x and y axis. So this whatever the result we get, whatever the graph you'll get, is called constellation diagram. So you can see in the constellation diagram, the real x-axis is the real part of signal, y-axis is the imaginary part of the signal, and we have various points in the red you can see. So each point here represent the signal with particular symbol. So that is, if I modulate a carrier with this symbol, what is the amplitude and phase is represented by this point. So if you modulate by 8 different symbols, the signal is represented in the constellation diagram by this graph. So the distance of a particular point from the origin represents its amplitude, and the phase actually represent the phase from the x-axis represent its phase of the particular symbols. Now this difference between the 2 points basically represent the noise immunity. What is the noise immunity is, as I mentioned before, the noise is present in the source as well as noise will be present in the amplifiers. So this noise can be intensity and phase noise. So if I transmit a symbol, and because of the noise, this symbol can move towards the other symbol. And this can cause at the receiver a very hard decision to make whether this is the 000 or 001. So it will be difficult to make a decision, and sometimes it can cause error. So in the presence of noise, there will be always an error. And in order to minimize the error or minimize the effect of the noise, we always try to increase the distance between these symbols. So the distance between the symbol basically represent the noise immunity. So higher the distance, you have more noise immunity and easy to recover the data. And so next one is, if you consider, based on this information, if you consider the ASK signal and BPSK signal. So ASK signal is like amplitude shift keying. So if you have a 1 bit or 2 symbol ASK signal, which means that you're transmitting 1 bit, means like either you have option of transmitting 0 or 1 at a time. So if you transmit 0 in ASK, it means you are not transmitting any power. When you transmit 1, it means you are transmitting some power. That's why it's called on and off. So in on-off keying, you can see the constellation diagram is one point is located at the origin, another point located at certain amplitude or intensity. However, in the BPSK, where you transmit 0, then we mean transmit certain phase. When you transmit 1, you transmit 0 phase. So this diagram represents the BPSK signals. And if you compare, the distance between the symbols in BPSK is larger than distance between symbols in the OOK. So this shows that the BPSK has better noise immunity as compared to OOK or ASK. So BPSK is usually preferred over the ASK. Now, our main aim is to transmit as much as data or at very high rate. That is our main goal. So in order to transmit high data rate over a particular bandwidth, we define a term which is called a spectral efficiency. A spectral efficiency shows that how much data rate we can transmit over a particular bandwidth. So in case of OK and BPSK, you see there is only two symbols we transmit per channel in a particular symbol duration. So sorry, there is two symbol or one bit we can transmit in particular symbol duration. So which means that spectral efficiency in both cases is very low. So in order to increase the spectral efficiency, what we can do in a particular symbol duration, we try to increase the number of bits. So if you try to increase the number of bits, means instead of sending one bit, you send 2 bits per symbol, that is the combination of 0 and 1. So it could be the 4 combination 0, 0, 0, 1, 1, 0, and 1, 1. So this is a case of QPSK. As we know that we don't use ASK, so now we try to move to the next level of the bits per symbol in BPSK, in the PSK system. So it will be called quadrature phase shift keying, and there will be 4 symbols we transmit, and each symbols are differed by each other by a phase of pi by 2. The intensity of each symbol, as you can see, lie in a circle, means it has a constant intensity. Only the phase differ by pi by 2. So this kind of modulation format will be called quadrature phase shift keying, because there is a 4-phase shift, and this is called QPSK. So as usual, if you see the number of bits per symbol is higher, so spectral efficiency will be higher. So it's better than BPSK. However, if you see the distance between the points, it's very small as compared to BPSK. So since the distance between the symbols are small, so it has lesser noise immunity as compared to BPSK. So it will be prone to more phase noise, and the chances of error will be higher at the receiver. We can further increase the spectral efficiency by going from QPSK to 8 PSK system. 8 PSK system means like you transmit 8 symbol, that is 3 bit at a time, 3 bit per symbol. So there will be 8 combinations, and each symbols will differ to each other by pi by 4. In this case, spectral efficiency is of course very higher than QPSK and BPSK, but the noise immunity is extremely low, and it will be so low to even to recover sometime. So practically, yeah.
Can I just want to mention that the last firmware of the AC1200 that does support again re-support the BPSK also. So the BPSK is actually the highest, the best performance for 100G application, and this is a rather new addition to our system. Okay, just want to mention.
Yeah, so actually we are going to discuss about there is a trade-off between the noise immunity and the spectral efficiency. Of course, this one will have a better noise immunity, so so again, if we can transmit at higher speed, if we can generate this data 0 and 1 at very high speed. So it's also depend upon how fast we can generate the symbols, and again, it's depend upon the DSP. It's depend upon the digital signal processing part. So we are going to discuss about those things.
Yeah, for 400G, this will be the best application, right?
Yeah, yes, that's correct. Because of the noise immunity, again, the receiver will be easy. I mean, the effect of noise will be lower, and the error rate will be very less in the BPSK. But never mind, even BPSK is used, still the COM QPSK is used, and even later on we are going to discuss even more and more higher. Of course, for AC1200 and 400G, BPSK will be used, but there are various higher order modulation format is still in use, in spite of it has a very lower noise immunity. But the digital signal processing part will take care of the noise issue or the error issues as well. Of course, there is always a limitation because of the electronics involved in DSP, so data rate will be lower in the higher modulation format in certain sense. So, so at PSK, as we see, like it has a lower noise immunity and mostly not in used. So what we learned from this slide is BPSK is better than ASK in terms of noise immunity, and increasing the bits per symbol will basically increase the spectral efficiency, but also decrease the noise immunity. So how to increase the higher number of how to increase the spectral efficiency, that is the number of bits per symbol. So one option is in the at PSK, the problem is the distance between the symbol is lower. So we can eliminate this problem by using the QPSK, but using two QPSK. One QPSK has a smaller amplitude and another one has higher amplitude. So basically what we are going to use, we are going to modulate both amplitude and phase in a way that it has the better separation between the symbols, but the intensity will differ from each other. So it will be not the only one amplitude, two amplitude, but also there is a phase variation. So it will be called quadrature amplitude modulation and vary in both phase and amplitude. So basically, if you consider 8 QAM, which is equivalent to 8 PSK in number of symbols, we will find that it's a 2 QPSK with different amplitude. But since it is QPSK, so its the noise immunity is better than the 8 PSK system, and also the spectral efficiency in terms of that, it will be equivalent to 8 PSK. Not only that, we can go further and we can generate the 16 QAM. Of course, 16 QAM contains 8 PSK and at the two amplitude levels. The noise immunity will be again lower than the 8 QAM or 8 PSK, but the spectral efficiency is very high. And later on, we'll discuss about the various possible sets to way to generate 16 QAM. And we can go so on, and we can theoretically use MQAM. MQAM is like use higher and higher number of symbols. So you can transmit B bits. So if you transmit B bits, essentially it will give 2 to the power B symbols. That is, we use the symbol M to notice 2 to the power B, and so it's called MQAM. So higher number of symbols per number of bits per symbol will definitely increase the spectral efficiency. Whether we use it or not because of noise immunity, it's another issue. So in a one symbol duration, that is TS, we actually transmit B bits for MQAM. So if you find out what is bit rate, the bit rate is equal to number of bits we transmit per symbol divided by symbol duration. That will be the bit rate or line rate. So number of bits per symbol will be log 2m. That is, if you take a log here, it will be log 2m divided by TS, the symbol duration. So which is equivalent to 1 by TS is symbol rate, or symbol rate is also called baud rate. So bit rate will be equivalent to number of bits time baud rate. Now here is the different comparison of different higher order modulation, the spectral efficiency, and of course the OSNR penalty. So you can see the binary data, that is OK and BPSK or DPSK, has small spectral efficiency. But we go to multi-level, that is higher order modulation, you can see the QPSK and QAM have higher spectral efficiency than BPSK. And further, the QAM has better efficiency than PPSK. Here we use a term called DPQPSK, that is dual polarization. As we discussed that we have another degree of freedom called polarization shift keying, and this is so in this case, like we basically use two QPSK, not in terms of amplitude. The amplitude of the QPSK is the same, only they use at different polarization. So the spectral efficiency will be doubled because we are using two QPSK. Similarly for the QAM, 16 QAM has spectral efficiency 4. When you use DP16 QAM, it will double the spectral efficiency. But in terms of OSNR penalty, you can see the ASK has higher OSNR penalty as compared to PSK system. And in PSK also, if you see if you increase the number of bits per symbol, the OSNR penalty is increasing. But in the QAM, which uses both ASK and PSK together, has lower OSNR penalty as compared to the PSK and ASK. So QAM is preferred over other two. So what we learned so far is increasing the bits per symbol will definitely increase the spectral efficiency, but it's also decrease the noise performance or increase the OSNR penalty. So a trade-off between the two is required, like how much you can sacrifice your receiver in order to send high data rates, or how we can receive even then. So if you remember this formula we discussed, the bit rate is equal to number of bits per symbol into the symbol rates. So let's see, let's verify this formula, and we all know this AC1200 parameter so far, which is commonly used in our lab, and this is the table given by AR. So you can see there is symbol rates, there is bit per symbol. For example, this one, the symbol rate is 34.72, the bits per symbol is 2. So essentially, if I use this data and to calculate the bit rate, it should be 2 times 34.72, that is 69.44 GB per second. But actual line rate you can see is 100. So how can it is higher than the actual bit rate we get from the formula? This is because when we transmit the data, we don't just transmit the information, which is also called payload, but actually you transmit various redundant data, which contains the source address, destination address, and of course, since we are going to encounter the errors at receiver, so we'll send the error detection and correction codes. So these are the redundant data, but it's needed in order to receive the data correctly. So that's why the number of bits we are going to send is actually higher, and so we need it's the actual transmitted data rate will be higher than the what we estimate from this formula. There is a various way to correct and detect the code. So in the optical communication, the one we use is called forward error correction. We add the redundant bits to the actual data, and using this redundant bit is actually coded in a particular protocols or particular algorithm, and at the receiver side we know which algorithm is used, and we try to decode the redundant bits, and then according to that we'll find out whether data has error or not, and even if data has error, how we can correct it even using these codes. There are various forward error correction code, or that is called fake. There is various fake is used so far. The first one was generic fake, which was the first generation, which used the Reed-Solomon code. So it's common. It's commonly used in the RF communication earlier days, and then the next generation was enhanced fake, which is used for DWDM system for 10G and 40G. The first coherent fake was staircase fake, which is also hard decision fake. And this was used for 100G. The second coherent fake was for 200G, which is called open fake. The last one is concatenatic phase, which is third coherent fake for 400G, which is basically used in data centers. So these are the different fakes, and I have a slides for it, but I'm not going to discuss right now because forward error correction or fake we are going to discuss at the time we discuss about the DSP. So I'll leave this slide for that, but you can see the effect of different fake, and we can see that latest fake basically can having more the coding over rate, like that is how much extra bit you add is higher, but at the same time it gives you the better performance. The net coding gain, we'll discuss what is it about, is higher with the higher fake, like that is C fake or no fake, it is very high. So we are going to discuss this in the DSP part. So the next we're going to discuss about the multiple optical multiplexing. So far we have seen we have a channel, and we can modulate these channels using various way of the optical carrier. We have access to amplitude, phase, and polarization, or including amplitude and polarization together, that is QAM, and then we can transmit certain data per channel. But in order to increase the IP traffic, we multiplex actually various channels together, and that is called wavelength division multiplexing, which means that we are going to transmit various channels together, and we already know about it, that there is two type of WDM. One is called coarse WDM, that is CWDM, and dense WDM, that is DWDM. CWDM is used in older system, which uses 18 channel, which is 20 nanometer apart, and it contains from O band to L band, the entire various band together. Since it's contain both L band to O band, like it has very huge loss up to 1 dB per kilometer. And the transmission distance is very small, like unamplified transmission distance was even 20 to 30 kilometers, very small. And that time it was used for 10G Ethernet or 8G fiber channel for data center. But now we use DWDM. What is DWDM is we use only C-band, and we divide the C-band in a 0.4 nanometer apart, that is 50 gigahertz apart, and we use total 88 channel. If you consider the extended C-band, then there will be 96 channels. So there will be larger number of channel we use in C-band, but of course the distance between the channel is reduced, but it's still sufficient for our applications. It could be even 100 gigahertz. In this case, the number of channel will reduce to 44 or 48, or it could be 75. So number of channel is again 54, and so on. Since we are using the C-band, the losses will be very low as compared to CWDM. So losses are 0.18 to 0.22 dB per kilometer. And the unamplified distance is 80 to 100 kilometers in this case. It's used in all, including 100G and beyond. It's also used in data centers and on the applications so far. So one way to multiplex the different channels is use one of the way of doing multiplexing is to multiplex different channel using WDM, but we have another degree of freedom, that is polarization. So we can transmit the WDM channel in one polarization, and then again in other polarization we can transmit. So these two polarization are called X and Y polarization. Basically these polarization are perpendicular to each other, so they never interfere. So we can actually securely transmit the data without interfering and successfully receive it at the output in. So since we are using the two polarization, it's basically doubles the spectral efficiency. But there is another application of it. Another application is called polarization interleaving. The polarization interleaving is used when the channel is very noisy, especially the nonlinear effects are very high. In this case, to reduce the cross phase modulation, the cross phase modulation happens between the two channels. So if the two channels are the same polarization, the effect of cross phase modulation is very high. So in such cases, which is it's rarely used, but in such cases, if you want to reduce the cross phase modulation or nonlinear effect, basically we change the polarization. So alternately, we send the channels at different polarizations so that these two channels do not interact to each other, and so cross phase modulation is reduced. Yeah.
Is there a commercial solution for polarization interleaving?
I didn't find it yet. Although I didn't do very good search to find it, but I did.
Abi, I think that Acacia and other, I think that Sienna are also using it. They are doing some mix of polarization, and this is how they get additional bit or half bit. I don't have the exact details, but they are using it.
Okay.
It's not polarization interleaving, is it? It's a hybrid solution. Hybrid is a different solution.
Yeah,
I think.
no, hybrid is a different issue, but they're using also polarization. Yeah.
Okay.
Yeah, they're using.
Okay, so so far we discussed about various modulation format used in optical communication. We learned about what is constellation diagram, how they represent a symbol, how to read the constellation diagram, and why it's matter. And then we learn about higher order modulation, why higher order modulation increase the spectral efficiency. That is to say it can increase the data rates, but at the same time it pay a price and it decreases the noise immunity, and the noise performance is lower and higher order modulations. So it will require very advanced digital signal processing to actually receive the data for the higher order modulation formats. Then we learn about optical multiplexing. There's various way, WDM, and then the PSK. So next one is optical modulators, and the optical modulators are the way to generate the optical modulation formats. So we are going to learn about the three different optical modulators, that is phase modulator, MGDM, and IQM. So let's see what is the optical modulator and how they can use to generate the modulation formats. There are two types of optical modulator. One is called direct modulator, another is called external modulator. The direct modulator is to say that it's directly modify the laser, which means that if you want to transmit certain data, you just laser work on a principle that you apply a current and you get the optical power. So if you modulate the laser current by the data, actually you can modulate the optical power output. So to say that if you want to send the data 10, particular data 10, so you send either current or no current, and the output you get either optical power or no optical power. So in this way you can actually modulate the intensity. And that's why since you are modulating the intensity in a way that you are turning on and turning off, basically it's equivalent to turning on and turning off the laser. So that's why the ASK system, especially the 2 ASK system, is called on-off keying, because you are turning on and off the laser. But the problem with this modulation formula is that it has no access to this modulator is that there is no access to the phase of the laser. It can only access to the intensity of the power. So you can only do the intensity and power modulation. That is, OK is only possible. No phase modulation or COM is possible. Also, since there is a delay between the input current and the output power, so this delay actually can cause the a problem when you apply the higher data rates. So it causes a delay and overlap between the bits, so it cannot use it to transmit the high data rate, so it's limited to the low data rates. So the other solution is to use the external modulator. What external modulator means that you take a laser and the laser output power is coming, and then you pass this laser output power to an external modulator, which is basically a waveguide. And then you apply this to the external modulator, you apply a voltage, and this voltage can be controlled by the information you are sending, the bits. So you modulate the voltage, apply this voltage to the external modulator, and this external modulator actually modulate the laser phase, amplitude, and so on. So advantage of this type of external modulation is, of course, you can modulate every possible modulation format. There is no speed limitation because speed limitation is now only limited by DSP, how you generate the voltages, and by the external modulators. But of course, the response time is much better than laser, so it can do the modulation at very high speed rate. So it basically can do the modulation, all the modulation possible at higher data rate. So there are three different type of external modulator: phase modulator, Mach-Zehnder modulator, and IQ modulator. So phase modulator basically is a waveguide, which is made of the lithium niobate. Lithium niobate is an electro-optic substrate, which means that when you apply voltage, is basically can change the refractive index of the lithium niobate. So basically, we can apply our bits in terms of voltages, which changes the refractive index of the lithium niobate substrate. That is our waveguide. So when a laser passes through it, it basically see there is a change fluctuation of refractive index depending upon the data. And so when there is a fluctuation of refractive index, basically it changes the path length, and changing path length means you are going to change the phase of the laser. So basically we are going to modulate the phase of laser by applying the bits in terms of voltages to this electro-optic substrate. So this modulator basically do only the phase change. So it's called phase modulator depending upon the applied voltage. So you apply voltages depending on the data, and you get different phases. We can model this phase modulator in terms of equation, and you can see that the electric field output depend upon the applied voltage divided by a parameter which is called V pi. V pi is the voltage for which there is a pi phase shift. So if instead of V pi, if I put pi, instead of UT, I can put V pi, that is this particular voltage, the phase shift we got is pi. So V pi is the voltage responsible for a pi phase shift. The typical value of V pi is 3 to 6 volts, so you can easily, integrate in a PCB board or something. So this is the phase modulator. Now it can only modulate the phase. So how can we modulate the intensity? So there is a very common phenomena used in optics to convert phase into intensity, that is called interference. And also through the same phenomena, actually, we can also convert intensity into the phase. The first one, the phase conversion to the intensity, is we use to do the intensity modulation. But the second phenomena, which is also possible through the interference, is converting intensity to the phase, which is actually used in the receiver. So this part also we are going to discuss when we discuss the receiver. So basically, we use the interference effect to convert the phase convert the phase modulation from phase modulator to the intensity modulation. So the interference here we are going to use is called Mach-Zehnder interference. So this Mach-Zehnder interference actually use two phase modulator in parallel path. So a laser light divided into two parts. The power is divided equally, and then the two phase modulator driven by two different voltages, and when they combine together, basically the phase is eliminated and we get intensity. How we get it, you can see through the expression. So if you see the output power, the output power of the Mach-Zehnder modulator is equal to the phase change in the upper arm and the phase change in the lower arm. But if your power, if your voltage applied at the upper and lower arm are equal, that is, it's called push mode. When the voltage is applied are equal, then and also the V pi is equal, then what you get is simply these two added together and gives the phase modulation. So when you apply the equal voltages in the Mach Zehnder modulator, basically you get equivalent to phase modulator. But when you apply equal but opposite polarity of the voltage, what you get is adding the two phase modulator output with opposite phases. And when you add two opposite and equal phase, basically it's cancel out the phase effect and create the modulation. That is here you can see as a function of cos. So basically you can say the output power, output amplitude is equivalent to input amplitude plus into the cos of certain voltages. If you calculate the power, the output power will be input power in terms of certain function of cos in terms of voltages. So basically we are going to modulate the optical power at the output of MZM as a function of cos of voltage, and voltage depend upon the bit rate. So when we send your bits, actually you are sending in terms of voltages. So your P output is also going to change according to what voltage you apply. So your power is going to modulate. So it's called amplitude shift keying or OK. So this can be possible using the push-pull mode of Mach Zehnder modulator. So as we see that it can modulate either phase in push-push mode or only intensity in push-pull mode, but it cannot do this both together. So how can, but for the quadrature amplitude modulation, we need to modulate both together. So how we can do it together? The solution is again another form of interference, which is called IQ modulator. The IQ modulator uses two MZM in parallel together in one of the arm. There is a phase modulator which always provide a constant phase shift of pi by 2. So when we do so, the two Mach Zehnder modulator are basically used in push-pull mode. That is, these two are act as an intensity modulator, and there is a phase modulator which provide a constant phase shift of pi by 2. This constant phase shift of pi by 2 basically create a quadrature effect of the input laser light. So your laser is passing through here, and what we see that there is a phase shift. So it's basically the opposite pi by 2 phase shifted from the other arm. So for one arm is called I phase, another arm is called Q phase, and then we intensity modulate this I and Q and combine together to get the output. So it's this modulator will call I and Q modulator, IQ modulator. If you see the output power or output amplitude, you can say it's a combination of two cos, two intensity modulation, but one of them is multiplied with imaginary factor that is coming from the phase modulator. And so actually this imaginary factor says that output has a certain phase as well as amplitude. So if you can calculate the amplitude as this formula, but if you want also calculate the phase. So basically what it does, it actually create both effect, intensity and phase effect because of this phase modulator, and both of them are together. So it can use to modulate quadrature amplitude modulation. So basically this is the IQ constellation diagram you can get from IQ modulator, and you can see that using the IQ modulator you can reach any points in the constellation diagram, which means that you can basically generate all the modulation format, not only COM but PSK, ASK, everything, only single-handedly to the IQ modulator. But again, the IQ modulator is complex, uses so many phase modulators, as well as the driving circuit, electric signals will be complex, so it will be very difficult to generate these electric signals to derive the IQ modulators. But next we are going to see how we can actually generate this different COM and PSK higher orders using this IQ modulator or Mach Zehnder modulators. But before that, I like to pay another attention on another term. It's called pulse carver and impulse shapers. So basically, when you transmit a data from modulated data and transmit it through the channel, we never transmit a constant power. Even in the PSK, where we're supposed to have only constant amplitude, we usually don't do it, because if you send a constant power, your photo detector at the receiver is going to saturate, because there is always a constant power for phase shift keying. So instead of sending a constant power, basically we send the pulse, and the pulse means that actually instead of modulating the phase intensity of a constant output power of a laser, we actually modulate the intensity and phase of an optical pulse. So how we generate this optical pulse is very important because it affects the performance of an optical communication system. So for example, let's say if you're transmitting OK signal, that is on-off keying, and let's say we are transmitting 1, 0 and this pattern. So when you send 1, you actually send a power. When you send 0, you don't send any power. That is on-off keying. So now it depends upon how much, when you send 1, actually can you send the exact symbol in interval of 1, the entire power, or we use only a small time, a small bit interval of 1 to send the power, not the entire bit interval. So when you transmit the optical pulse in entire bit interval of 1 and nothing in 0, this is called NRZ pulse. This is called NRZ because it's called non-return 0. So in the symbol duration of 1, basically the optical power never return back to the 0. So that's why it's called NRZ pulse. While symbol 0 anyway has no power. So when there is a symbol transition from 1 to 0 or 0 to 1, what happened that there is an optical power decrease from high to low or low to high. So this decrease in the power with time can create chirping because the optical fiber has various nonlinear effect. One of them is self-phase modulation and cross-phase modulation, which basically depend upon how the intensity of the signal is changing. So this effect can be higher at this symbol transition because there is abrupt change in the power. So the slope, like the change in the power, will be high here. So the nonlinear effect or the chirping is very high. So NRZ pulse provide very high chirping, and which actually create a lot of problem in the system performance. So we never use NRZ. We forbid to use NRZ usually. Instead of NRZ, we use RZ. RZ is return to 0, which means that when you send a symbol 1, instead of sending the power in the entire bit duration of 1, we only use the half or certain percentage. So it could be either 33%, 50%, or 75%. In this case, we are sending 50% of the power, 50% time we use to send the power. So in this case, what happened that when there is a symbol transition, for example, 1 to 0, so you can see in the one time, or in the symbol of 1, also there is a power going to 0. So when there is a transition, there is basically no change in power trend happen at the symbol transition. So basically the effect of chirping or nonlinear effect is reduced significantly if you use the RZ pulse. And how we can generate this RZ pulse. So these pulses are, as you can see, is just an intensity modulation. So what we can do, we can use the Mach-Zehnder modulation in push-pull mode to generate the RZ pulse in the optical communication systems. But if you see closely at the Mach-Zehnder modulator, basically it gives you the intensity modulation, but as a function of cos, which means that our output power is never going to be a square looking power, but always a Gaussian shapes or cosine functions. So that's why our optical power will be a form of a Gaussian, or like a form of a smooth curve, as you can see. There is another advantage because of this, because there is a smooth curve. What we can see that the power transition here inside the bit duration also is having a very low slope as compared to this shape. So effect of nonlinearity is further reduced if you use MZM RZ pulse. So this is called pulse carver. The pulse carver basically consists of a MZM in a push-pull mode to create the MZM RZ pulses to reduce the chirping. But the chirping also depend upon the voltages you applied to the MZM modulator. So in all type of modulator, whether PM, MZM, or IQ, you always apply voltages. Now the shape of voltages, like when you transmit 0 or 1, what shape of voltages you apply to this modulator basically also affect the chirping. So we try to use these voltage shapes as a Gaussian like or similar to look like this voltage shapes to further reduce the chirping, and the exact element used to create this kind of shape is called impulse shaper. Basically, it's basically changes the shape of the voltage, so it's called impulse shaper. So the pulse carver and impulse shaper is very important in the optical transmitters to create a RZ pulse and transmit it through the optical network. So what we learn here is that external modulator is preferred over the direct modulators, because external modulator can do all kind of modulation, whereas direct modulation do only intensity modulation, while external modulation also operate at high data rate, while direct modulation cannot operate at. External modulator consists of three types. It's made of basically electro-optic waveguides, which is made of the lithium niobate or gallium arsenide and those kind of electro-optic substrates. There's three kind: phase modulator, MZM, and IQM, and these are used to generate the various modulation formats. We also seen that pulse carver and impulse shifters are used to reduce the chirping in the signal, and it's a very integral part of the transmitter. So next we are going to learn about the transmitters, how we use this optical modulator to create basically different form of modulation formats, and especially the higher order modulation, which is very important. So so let's talk about the transmitter. So for example, the first one is amplitude shift keying, that is ASK. So the simplest one is 2SK, or that is OK, which means it transmit only 1 bit per symbol, that is B is equal to 1. So symbols are 2, 0, and 1, which means when there is a symbol 0, we transmit no power, 1, there is transmit some power. The transmitter looks like this. We have a laser which give you the constant power. We use MZM RZ, so Mach Zehnder modulator, to do pulse carving to get a RZ pulses, and then another MZM is used to do the intensity modulator in push-pull mode. The data, which is the stream of bits, fit to the impulse safer, which created the voltages in form of Gaussian, which is applied to MZM to create the intensity modulator. So this is basically the transmitter for 2SK system or OK system. As you can see, the optical power at the output look like something like this. So in a bit interval of 1, there is no power in the entire bit interval, rather than almost half, and also the optical power looks like a Gaussian shape. Whenever there is a 1, whenever there is 0, we don't transmit anything. The next level of higher level of ASK is MSK, that is you transmit use more than 1 bit per symbol, that is 2 or 3 bits. But in order to do that, you need to transmit multiple power level. And when you transmit, for example, 4SK, you have multiple power level, like 4 power level. So it will be more prone to intensity noise, and intensity noise is always present in optical communication system because of the amplifier we use, which provide the amplified spontaneous emission noise, AC noise. So this cannot be used because of the AC noise causes the noise interference, and so this required a very high OSNR at the receiver in order to successfully distinguish between the two symbols. So it cannot be used usually. I mean, the standalone, the ASK is not used at higher level. So another format is PSK, the phase shift keying, which basically the simplest one is BPSK, which means like there is only 1 bit or there is 2 symbol. So when you transmit 1 bit or 2 symbol, which means like you're transmitting either 0 phase or pi phase. Next level is B equal to 2, that is quadratic phase shift. So you're transmitting the 4 symbols, combination of these 2 bits, and each symbol differ by pi by 2. In general, if you go so on, for 8 PSK, it will be difference with pi by 4. 16 PSK is difference between the symbol is pi by 8. In general, if you transmit like B bits, the difference between the 2 symbol is pi by 2 to power of B minus 1. So using this formula, actually, you can calculate how much the phase difference at the higher order PSK systems. There is an interesting thing in the PSK is that instead of when you encode the bits, instead of encoding directly, we can do the differential encoding. Differential encoding do help a lot in the noise, in the presence of phase noise, because let's say if you're transmitting the BPSK signal, so you're transmitting actually 0. When you transmit 0, actually you do a phase change of laser by 0 degree. That is no phase change. And when you transmit 1, basically you create a pi phase change of the signal. But having doing so, we actually send 0 and pi phase of laser, but when there is a phase noise present, and let's say the phase noise is extremely high, and somehow the 0 goes to one side, the phase changes opposite way, so we cannot recover the 0 at receiver, so it's more prone to the phase noise. So instead of doing the absolute phase change in the laser in terms of the bits, we do the differential change. Differential change means we do no phase change of laser when there is no bit change. So we have a 0 1 0 1 data coming. When there is a 2 consecutive bits are 0 0, we do no phase change, or when there is two conjugative bits coming as a 1-1, there is no phase change. And we apply phase change only when there is a bit change. So when the bits are like 0, 1, 1, 0, something like that. So whenever there is a change of from 0 to 1 bit, we send a pi phase shift, or 1 to 0, that is we send pi shift it. Otherwise, we don't change any shift of the layer. In this way, actually, we reduce the effect of phase noise, and basically so that's why the DPSK perform better in terms of phase in presence of phase noise than BPSK. So DPSK sometimes is preferred over BPSK, but again, DPSK require a little complicated electrical level signal generation, because in BPSK you just use 0 and 1 to generate voltages, but here you need to check the previous bits and compare with the present bit, and then only you can change the phase. So generating voltages depend upon the bit stream. So generating the DPSK electrical level signal is complicated than BPSK. So that's the another one disadvantage of using DPSK.
Abi,
Yeah.
it's too fast for me. I don't know about everything, about everybody. Can you slow a bit?
Oh, sure, but I hope you could have told me before, because I thought everyone is understanding.
As a joke, I thought that my wife is speaking fast, but now I see that you broke the record, but just as a joke.
Okay, so but can you
A bit slower, because
okay.
I have to observe it and to understand.
Okay, I'm sorry. I'm sorry,
Thank
but
you.
I wish you could have told me before. I would
No,
have
it
slowed
was
down.
up to now. It was perfect,
Okay.
and continue like this, but a bit slower. Thank you.
Okay, fine. So, so I hope you understand BPSK and DPSK, why DPSK is preferred over BPSK, and why it's complicated. Also, it's complicated because the electrical level generation is difficult in DPSK as compared to BPSK. When you see the bits, when you see the bit symbol assignment, for example, BPSK is simple one. You either transmit 0 or 1. In terms of QPSK, you see it's, you transmit 0, 0, 0, 1, 1, 0, and 1, 1. In at PSK, again, it's 3 bits, and so you have various combination of bits. So in a constellation diagram, how we play with this different symbols, like different bit combination, is very important. So if in a constellation diagram, for example, here, the conjugative symbol only differ by only 1 bit. For example, this symbol and this symbol only differ in the last bit. It's only changes 0 to 1. And here in the downside, you see again there is only change in 0 to 1. So if any conjugative two symbols differ only by 1 bit, for example here they differ only in the last bit. Here it's only differ in the first bit. Any two conjugative symbol you take, it's only differ by 1 bit. It will perform better as compared to the places where the symbol differ in 2 bits. For example, I don't see any example here. For example, if these two symbols are nearby each other, there is 2 different changes. So as compared to this two where there is only 1 bit change, and if you keep this here, there will be 2 bit change. So at the receiver, this one will perform lesser as compared to the symbol where there is only 1 bit change, because in a system, in an assignment system of constellation diagram, when the symbols differ only by 1 bit, or as minimum possible bits, the effect of noise, even it comes in one of the bit, it is minimum. But when there is more changes in the bits, it will be maximum. So effect of noise is basically reduced if you create a constellation diagram by means of transmitter where the different symbol differ from each other only by 1 bit. And this way of assignment of symbols where everything is differ in conjugative symbols only by 1 bit is called gray coding. Gray coding gives us a better noise performance as compared to the normal coding. And so we'll see in the transmitter side how we do the gray coding. So the phase shift keying, as usual, it's do the phase shift. So we can use the phase modulator, because phase modulator is optically very simple than IQ modulator. IQ modulator.
Yeah. Sorry. Okay. When is this gray coding included? Where do you see it happening? I know from Palm 4, but
So we'll see here, for example.
But again, it's only related to currently. It's only related to PAM4, or it's related to a lot of
no,
other modulation formats.
no, I think it's a lot of other modulation format. For example, even in the QAM, the gray code is used. If you look closely at the different symbols, even in the QAM, 16 QAM, even 32 QAM, the gray code is used because
How do you know? How do you know? How can I know if it's included or not? Other than
so just check different. If you check the constellation diagram of
the constellation only, huh? Okay.
yeah. So constellation diagram, you check and compare any two consecutive bits symbols and compare the bits order. So for example, this three, if you check this three, from here and here there is only last bit change, only one bit change. From here and here also only one bit change. That is this second bit change.
Yeah, I understand. But in order to do to see that, I need a constellation analyzer and a very good analysis. Yes.
Yeah. That is of course unfortunately needed to find out whether the Greek code is or not. But most of the most of the companies use it because it's not very first of all, it's, as you see, we'll see in the later on that it's not very complicated to generate. Even the electrical level signaling is not difficult for gray coding, and it's quite natural to do it. So people, I mean, most of the companies actually use it. Most of the vendors use it to do the gray coding. For example, the phase shift keying. So we know that phase modulation we can do the three way. Like either we can use phase modulation, you can use Mach Zehnder modulator in push mode, or IQ modulator also do the phase modulation. But out of three, the phase modulator is the simplest one in terms of optics. So we can use the phase modulator to generate the phase shift keying. Now, here I'm presenting a transmitter which can be used to generate MPSK, like higher order PSK, but it can be applicable to any one of them. So for example, if you have what we use different phase modulator in series, and each phase modulator provide a phase shift of, first one provide phase shift of pi, next one provide 5/2 phase shift, next one provide 5/4, and so on. So each phase modulator basically provide a phase shift of pi/2 to the power of m-1. M is the number of bits per symbol. So that's how that is the function of each phase modulator, and these phase modulators are in series to each other. So this combination of phase modulator is called serial transmitter because all the phase modulator are in series. So, and these phase modulator are driven by the electrical signals, that is voltages, and these voltages are generated from the data. So when data is coming, you demux data is coming in a serial way, that is a stream of 0 and 1. You demux this data to create the parallel data. Basically this is serial to parallel converter to convert the parallel data. And if you're doing the differential encoding, which is not necessary, but if you can use the like DPSK, then you do the differential encoding, and this differential encoded output signal bits actually used to give to the IS, that impulse stepper, which create the voltage shape, and then which drive the different phase modulator. Again, the first MZM RZ is to create the optical pulses. So as you can see here, even it's a phase modulation, that is the intensity is supposed to be constant, but basically we never use the constant amplitude. We use MZM to create the pulse and then modulate the phase of this pulse using various phase modulator. So for example, if you want to use BPSK signal, generate the BPSK signal, what you need is you have only one bit per symbol. So you use only one phase modulator, which either provide 0 or 5 phase shift, so you get the opposite phases. But in case of QPSK, you have 2 bits per symbol, so you need 2 phase modulator. The phase modulator provide pi and 5/2 phase shift. So in this case, when you pass, so in this case, let's say how you generate the different symbols. So when you have a 0 bits, so here you apply 0 voltage, you basically see there is no phase change in the pulse. But when you apply 0 and 1, so there is no phase shift here because it doesn't provide any phase shift. You apply 0, and here you apply 1 bit, so you get a phase shift of pi/2. So 0 and 1 give you the phase shift of pi/2. In case of 1 and 0, when you apply 1, 0, what will happen? Actually, in case of 1 and 0, this one activate and this is deactivate. So this provide only phase shift of pi. So 1, 0 give you the phase shift of pi. When there is 1, 1, that is the 2-bit symbol. So it gives the phase shift of pi and pi/2, that is 3 pi/2. So you reach all the constellations points. So all the symbols can be generated using the combination of two-phase modulator for QPSK signals. And those are these phases, as you can see. So again, when you don't need differential indicator, because when you don't use DPSK signal, then this part can be removed and all the bits directly fed to the impulse zipper. So this is called serial modulator and serial transmitter. Serial transmitter uses the series of phase modulator. There is another transmitter which is called parallel transmitter. In the parallel transmitter, basically we use one IQ modulator and then rest of phase is phase modulator. So when you transmit m bits per symbol, basically we use one IQ modulator, and since IQ modulator contains two MZM, so it replaces basically two phase modulator. So instead of first two phase modulator, we have IQ modulator, and then the rest there is m-2 phase modulators. So in the minimum case, since we have, and if you remove all the phase modulator, we have only IQ modulator present. So the minimum case in this case is QPSK. So you cannot generate BPSK through the parallel SIM transmitter. You can only generate QPSK and higher order. So if you generate the QPSK, again, you do the similar coding as it is here, and then apply to MZN or phase modulator on the electrical signals. Now, if you use only, let's say you have to generate only QPSK, so you don't need phase modulator, only the IQ modulator, you remove this part, and then you apply the symbols. So it happens to, in the IQ modulator, since you apply in phase shift of 90 degree, so because if you do the calculations and everything, because one arm is without phase shift, another arm is phase shift. So at the output, basically you are providing, if you combine both together, a phase shift of multiplication of pi by 4. So when you do a constellation diagram mapping through this IQ modulator, basically you do a constellation diagram like this, which is a pi by 4 phase shift from the serial transmitter. So the serial transmitter, the parallel transmitter, basically you for the QPSK, it provide the uses only one IQ modulator, which is in parallel, so it's called parallel transmitter, and basically it's shifted the phase of the constellation diagram in multiple of pi by 4. So that's why you see both are QPSK, but one has very perfect 0 pi by 2 phases. Here is always in terms of pi by 4 because of the IQ modulator. Again, whether you need differential encoding or not, depend upon whether you are using PSK system or DPSK system. So we have two transmitters, serial and parallel transmitter. In terms of the noise performance, the constellation diagrams, they both are equivalent, except that both are shifted by pi by, one is shifted by pi by 4. But in terms of performance, it's supposed to be same, but basically it's not same. So when you compare the performance of the serial and parallel transmitter, here I include the graphs for both serial transmitter, which uses NRZ and RZ signals, and parallel transmitter with the NRZ and RZ. So as we discussed, RZ perform much better in terms of chirping. So here we consider the effect of chirping, and this is the product of chirping and intensity. We can see that RZ transmitter has lower chirping than NRZ in both serial and parallel case. But if you consider the serial transmitter and parallel transmitter, the parallel transmitter has almost no chirping, whereas serial transmitter has still a little bit of chirping. So what we conclude is that parallel transmitter has almost no chirping as compared to serial transmitter. So the parallel transmitter is preferred over the serial transmitter. So if you want to generate a PSK signal, what you need is a parallel transmitter using a IQ modulator, because it has a better performance. So whenever you do the QPSK modulation or QPSK transmission, basically we always encounter this constellation diagram than this one, which is pi by 4 shifted because of its performance. Again. So next one is QAM. How this is one of the important modulation format, and we have learned that the QAM actually modulate both and phase and intensity together. Again, what we have learned in the past slides, that QAM has lesser number of phase state than equivalent PSK system, so it will perform better in terms of noise. However, in terms of spectral efficiency, it will have the same spectral efficiency of the PSK system, but the noise performance is better, so QAM is preferred over the PSK. So for example, let's say the QAM here, it's a 16 QAM. So 16 QAM consists of basically 8 PSK system. So each PSK system is only differ by intensity. Other than that, the phases are almost same. So this type of constellation diagram or this type of QAM is called a star QAM, because it looks like a star. The constellation points looks like a distributed in form of a stars. So it's called a star QAM. This star QAMs only have concentric circles, and these circles represent the amplitude. However, phase in the two concentric circles are almost always same. So the phase of this symbol and this symbol are same. It's only different in the amplitude. Similarly, here and here is the same phase but different in amplitude. So the star quam have concentric circle means the phases are equally distributed. Phases are equally distributed, only different in the amplitude of the two circles. But there is a problem. The problem is the distance between the symbols are not same always. So here is the distance between the outer circle is higher than the lower circle. So the noise performance here is better than here. So this means this system, the StarCom system, is not optimal in terms of noise performance. Somewhere is low, somewhere is high. So it's a problem because your noise performance can be optimized in a better way. So one way to optimize the noise performance is if we take some symbol from inner ring and create another ring at outside. So that is the square cam. So you can see the inner ring, which is here 8, we take out the four symbols from here and create another ring and the outer layer, which contains this 4 symbol. And the middle layer, the middle ring is same as this one. So when you do so, when you take out the four symbol from the inner ring and put at create another ring, while we do so, actually we create a symmetricity in terms of a square. So basically, if you see, it becomes a square. So it's become a square sub-constellation modulation, which means that distance between the two symbols are always constant. If you consider any two symbols, the distance are always constant. So in terms of noise performance, it is optimal as compared to the StarCom. It has equal noise performance for every symbols. So this is the optimal noise performance. However, it create another diagram which looks like a square. The constellation diagram looks like concentric square. So this is called a square quam. The square quam always perform better in terms of noise than a star quam. However, again, while we are doing so, we basically what we did, we took 8 PSK system from the inner ring and converted it to the inner ring of QPSK and another outer ring of QPSK. So while doing so, what we did, we created, instead of 2 intensity level, we created actually 3 intensity level. And also we additionally created different phases. So now here the only phases are 2, like the concentric circle has same phases, so it's different on only the 2 phases. But here actually we created multiple phases. For example, here this is another phase, this is phase. These two are symbol same, but these are different. So here, if you see the in terms of number of phase, it has only 8 phases and 2 intensity level. Here you have 3 intensity level, but number of phases are 12. So both number of phases are increased, number of intensity are increased, but it performed the better in terms of noise because of the separation between the symbol is optimal. But since it has more phase level now, more intensity level now, the optical transmitter will be complicated for a square quam than a star quam, and it's also very difficult to generate. It was so difficult that it took a long time to actually use a square quam. Currently, it is in practice, but it hasn't been used until the high-speed digital signal processors came to the existence, and then only we started to use the square quam. Because of the labor of electric electric circuits will be so complicated to generate these symbols because it has 3 different intensity level and higher number of phase levels. So we'll discuss about how to generate this both star and square quam. So first one, we'll discuss about the star quam. Of course, the star quam have concentric circles. It's always lie in circles. Each circles only differ by intensity. The phases are always same. So for example, if you want to generate a 16 quam can be generated in 2 possible ways. One way is, of course, use a PSK system and having 2 different intensity level. So basically it will be 8 and 8, total 16 symbol. So it will be 16 quam. There is another possible way, use the QPSK. So QPSK has 4 symbol, and so you need to use the 4 intensity level. So 4 ASK and QPSK system is also equivalent to 16 quam because it has 16 levels, 16 symbols. But if you see in terms of phases, the phases in the 16 in this system, the 4 ASK QPSK system, are apart than this system. the 8PSK system. So in terms of phase, it looks like it performed better. So phase noise looks like it performed better. But in terms of intensity noise, since this system has only 2 levels, here is 4 level, so intensity noise has very high impact here. So the 4ASK QPSK system performed better in terms of phase noise, but it performed very poorly in terms of intensity noise. And there is a lot of intensity noise present in the communication system because of the amplifier. So the lower number of intensity level is always preferred over the phases, lower number of phase states. So since this one has a lower number of intensity state, so this constellation diagram is preferred over this one. So basically, if you generate 16 QAM, we are going to use 2ASK 8PSK system rather than 4ASK QPSK system, because overall the noise performance of this one will be better than this one. Again, so if you want to generate a 16 QAM, and we are going to use 2ASK 8PSK system for generating 16 QAM, we can do in a two-way, like for the phase modulation, serial transmitter, and the parallel transmitter. So in the serial transmitter, it's very similar to the PSK. We can generate 8 PSK and then we can do intensity modulation. So the serial transmitter consists of 3-phase modulator to generate 8 PSK system. And then at the end, we use an intensity modulator as a MZM. So MZM is used to create another intensity level, but with the same phases. So it will be very simple. Similarly, in terms of parallel transmitter, we use one IQ modulator and one phase modulator to generate the 8 PSK signals. And then we use another intensity modulator, which is used as MZM is used for intensity modulator, and this intensity modulator actually modulate the intensity to create this constellation diagram. So here we're going to see the serial transmitter. Serial transmitter, again, only 3-phase modulator for 8 PSK, and the last one intensity modulate for 8 PSK for the intensity modulation to create the another ring, another intensity level. So the last bit is actually used for MZM. The first 3 bit, again, either differentially encoded or not, if you prefer differential system. And then it's given to the impulse shaper of the phase modulator. Last one is given to the MZM impulse shaper. And then it creates the 8PSK system. There is important parameter which is called ring ratio. The ring ratio is that what is the intensity of outer ratio divided by inner ratio, and it's play a very crucial role in OSNR performance, because if there is a higher ring ratio, means the 2 levels separated by a huge amount, which means the impact of intensity noise will be lesser. So OSNR requirement will be lesser for if the ring ratio is higher. When ring ratio is lower, the OSNR requirement is higher. So this play a bigger role. In parallel transmitter, instead of 2 PM, we have IQM, IQ modulator, and rest of them is same. Again, since we are using the IQ modulator, it provides the pi/4 phase shift, multiple of pi/4 phase shift in constellation diagram. So if you see these two closely, actually it provides multiplication of pi/4 phase shift between the constellation diagram. For example, you see the all 0 lie on x-axis in the serial transmitter, but all 0 actually lie at 5 pi/4 here in the parallel transmitter. This is because of the IQ modulator we use in the parallel transmitter. However, as we've seen earlier in the PSK system, the parallel transmitter has better chirping, lower chirping and better chirp performance. So parallel transmitter is always preferred over the serial transmitter. I hope the speed is better now, or I'm going so fast.
Abi,
Yeah.
do you know which one Acacia uses? Is it parallel?
No, neither of them. It uses parallel, of course, but it doesn't use a star. It uses a squark one. So right now we're discussing a star. So we're going to discuss a square. And of course,
parallel is actually extra cost, right?
We'll see in the square cam, actually parallel is lower cost, not lower cost, but the parallel is more easy to generate than the serial in terms of square. Here parallel is difficult to generate because of the IQ modulator, but there it perform better performance. The parallel do better performance, not only in terms of chirping, but also to generate electrical level signaling. So that's why they use the parallel square com in Acacia.
Okay.
So we are going to see the Squarcom, and I hope the speed is okay. If not, then you can tell me. So Squarcom, as we learned that a square com is not a star quam. It doesn't have the concentric circle, but instead of that, it has concentric squares, and everything has a separated equally. All the symbols are separated equally. So because of that, the noise performance are optimum because of the equidistance. Since in the square quam, in the star quam, basically in the star quam, we can generate a PSK and just change the intensity using a MZM. So generating a star quam was very easier in terms of optically and electrically, because you just need to generate PSK and use another intensity modulator. But here, it's not the same, because now we have not only here in terms of star quam, we have 8 phases and 2 intensity level, but in the square quam, it's complicated because it has now 3 intensity level and multiple phase levels, which are also not the similar. So here the outer and inner ring has a similar phase. That's why you can just use an intensity modulator from at PSK. But here the inner and outer ring has no similar phases, so it's very complicated. You cannot just generate a PSK and do an intensity modulator. Basically, you need to use a different scheme to generate the square quam, and it's very complicated than a star quam. Again, the square quam consists of 2, serial and parallel, and serial transmitter consists of only one MZM and one PM because it's serial. So both MZM and phase modulator are in series to each other. MZM provide the intensity modulation and phase modulator provide the phase modulation. In parallel square quam, there is only one IQM which provide both intensity and phase. How? We'll see it. So serial transmitter, as we discussed, that it has one MZM and one phase modulator. One MZM provide the intensity modulation and PM provide the phase modulation. So MZM, which provide the intensity modulator, basically it provide all the 3 level of intensity. And so you remember that MZM push-pull mode, basically if I go back, you can see the optical power depend upon UT. And so if you change the UT, actually, if you put it 0, you get minimum power, you get higher, then get higher power. So depend upon what the voltages you provide, actually you can create multiple intensity. So it's not necessarily the 2 intensity. If you provide multiple voltages, you create multiple intensities. So that's why it's used in square quam. We use only one MZM to provide the multiple intensity. For example, here 3 intensity level, we can generate through the only one MZM. But since we are using only one MZM and creating 3 intensity level, the electrical signal should have the 3 voltages. In normal way, you can say the electrical signal should have the 3 different voltages level to provide the 3 power output from MZM. So you need to create 3 voltages from the bit stream which is coming. So you can see the last 2-bit stream is used to generate the intensity, and we need a label generator, a combination of logic circuits and as well as the different electrical circuit to generate the labels from the bits. So it will be a complicated circuits to generate the 3 labels from the 2 bits. And so electrical signal generation is complicated in this case. Similarly for the phase, you need to generate now not 8 phases, but actually 12 phases. The 8 phases here and the 4 phases here, because outer ring and inner ring has similar phases. So 4 phases here and 8 phases here. So overall, you need to generate 12 phases using one phase modulator, and you have 2 bits for that. So you need to do, if you need differential encoding, we need it, otherwise not. So we need to generate this different voltage level, like 12 voltage level from 2 bits to create 12 phase levels. And since we are using only one phase modulator, so this level generator is going to be very complicated to drive the MZM and phase modulator to create the intensity and phase modulation. So electrical driven circuit is very, very complicated, and it requires complex electrical level generator. And whenever there is a lot of electronics involved, what will happen that it always provides the speed limitation, because all the electronics has a delay. All the electronics element has a delay, and so it cannot operate at high data rates. So because of the complicated electronic level generator, this is not practically in use, and this is one of the reasons the square quam was not used, and it's only started recently. Not used. The system was given long before in 1962 2002, the square QAM formats were proposed, but not been used for a long time because of the DSP, the digital signal processing, and all the circuits elements were not very fast. So this required a complex level generator, complex electrical circuit, and which cannot work for high data rates. And our main aim is to generate the higher order modulation to support the high data rate. So the serial QAM is not used. So serial square QAM is not used. What is used is parallel square QAM. In parallel square QAM, instead of using the MZM and PM, we use just one IQ modulation. Now, if you remember the IQ modulation, it basically can create, when we go back to IQ modulator, you can see IQ modulator basically consists of 2 MZM and provide a phase shift of pi by 2. Basically, we can reach any point in the constellation diagram in form of a square shape. So it provide, the IQ modulator basically provide a symmetricity in terms of X and Y axis. So the IQ modulator has this inherent property because of this formula, because of its symmetricity of the X and Y axis. It has an inherent property to provide you the constellation diagram, which is symmetrical about X and Y axis rather than in terms of rings. So a square QAM is basically symmetrical about X and Y axis. You can see it's a symmetrical squares. So it can be easily generated from the IQ modulator very easily without having a complicated electrical level generators. So there's, you can see that there is a concentric squares which is symmetrical about X and Y axis. So it can be easily generated. So one IQ modulator is enough to generate any level of MQAM, square MQAM. For example, here is 16 QAM. Again, the electrical level, it required because there is only one IQ modulator to generate different phases and intensity here as well. So it will require a complex electrical circuits to generate this voltages here, this 2 point. But this voltages will be this electrical level circuitry is complicated than the PSK system, but it is less complicated than the serial square QAM because of the IQ modulation. So the electrical level generation, electrical complexity of the circuits will significantly reduced because of the IQ modulation than the serial transmitter. Further, we see that always the parallel transmitter, because of IQ modulation, has lower chirping. The effect of chirping is reduced in the IQ modulation. So parallel transmitter anyway preferred over the serial, as well as it provides the less electrical complexity, so work at high data rate. So we always use parallel square QAM, which is basically the IQ modulation. So now everything is limited to only IQ modulator. If you want to generate the QAM, we don't need MZM, don't need IQ modulator, phase modulator. We just use one IQ modulator to generate the square QAM. The only difference is you need to create a huge different voltages level and the complex electric circuits. So again, since now we have a high-speed DSP, it's easy to generate these days, and so the square QAM is preferred, and the parallel transmitter, that is IQM, is used to generate the square QAM. So what we learned so far today is in this section is that higher order modulation basically increases the spectral efficiency but decreases the noise performance. PSK perform better than ASK for the same number of bits per symbol. So if you want to use, but you cannot go increase the PSK system for more than 2, because if you use 8 PSK or 16 PSK, the noise performance is significantly reduced. So if you want to use bits per symbol greater than 2, basically QAM is preferred. So 8 QAM, 16 QAM, 32 QAM, even 64 QAM, even up to 8 bits, that is 256 QAM is reported in the literature. Not used practically, but at least reported in the lab to use it. It has a very high spectral efficiency, of course. So the parallel transmitter we have seen in all the cases, whether it's phase modulator, whether it's ASK, PSK, or QAM, always preferred over the serial transmitter because of the chirping. And parallel transmitter always include IQ modulator. So IQ modulator is very important. We have seen that a square QAM perform better in terms of noise as compared to a star QAM, because a square QAM, the constellation points are equally separated. So the performance of noise is equal for all the symbols. So it's optimal. At higher data rate for greater than 100 Gbps, we use actually a square QAM, and so since a square QAM is generated by IQM, so IQM, the IQ modulator, is used for greater than 100 Gbps data rate generation. Later on, we are going to learn that demodulating the square QAM is never simple, because here the star QAM, you just need to when you want to demodulate, you just need to detect the phases, and the intensity is just a decision whether high or low intensity. So if you detect the phases, it's very easy to detect the star QAM. But in a square QAM, since the phases are not symmetric and they have different intensity level, it cannot be detected just using a direct. Yeah. Yeah. Yeah, I can hear you.
Abi?
Yes.
Abi, do you hear me?
If you're talking to me, yes, then I hear you. Hello. Hello. Can you hear me? Can you hear me?
Hello, I hear you, but seems Amir doesn't hear you.
Maybe he can write.
Okay, so let me check if he writes something. Yeah, someone wrote something. Yeah, so there is nothing I can see. So we'll continue. And Amir, if you can hear me, you can write something, because we don't hear you. I can see you are speaking, but we can't hear you. Okay, so I will continue. So as you see that square QAM is easily generated in terms of electronics than a star QAM. But in terms of receiving, the star QAM is easy to receive because you have a PSK system and then intensity modulation of the PSK system. And since phases are symmetrical, you just need to detect, like simple, you have a phase detection, and then you just do a hard decision on the intensity, and basically you can detect the star QAM. But in case of a square QAM, you can do the direct detection, because direct detection is not possible because of different level of phases and different level of intensity as well. So what the square QAM need is coherent detection. So a very special receiver is used to detect the square QAM, which is called coherent receiver or coherent detection for demodulation. We are going to learn about the coherent receiver. But since the coherent receiver is used for a square QAM, so square QAM is basically called coherent modulation format. So any higher order modulation QAM is called coherent modulation format because the coherent receiver is used to demodulate it. And the communication system which employ them for a data rate of 100 greater than 100 Gbps is called coherent communication. Why coherent communication? Because again, it require it, because in this communication system, if you want to transmit more than 100 Gbps, you need to use a square QAM, and at the receiver, you need coherent demodulation to demodulate this square QAM. So the communication system itself is called coherent communication. So next we are going to discuss optical receiver, but I think I'll just introduce it, but I'm not going to discuss it today because I think it's I discussed so many topics today, and I'm going to discuss the coherent optical receiver together with the DSP in the next session, and I'll try to follow entire thing about the DSP and about the coherent receiver. But just to introduce what is coherent receiver is, what is the receiver is, like at the receiver we are going to detect the different modulation format. So there is two ways to detect the modulation format. One is called direct detection, another is called coherent detection. So direct detection and coherent detection both can use to detect the variety of modulation format. For example, direct detection can use to detect ASK, PSK, and star QAM, but it cannot detect a square QAM. Square QAM only detected by coherent detection. So coherent detection again can detect all type of signals, but there is two different kind of coherent detection. One is called homodyne coherent detection, which detect ASK, PSK, and STARCOM. And then there's something called homodyne synchronous detection. The synchronous detection is used to detect the square-com as well any other modulation formats. So next session, we are going to discuss both direct detection, coherent detection, as well as the DSP part of transmitter and receiver both. But remember, as we discussed in the modulators, the main principle in detection is this one. If you want to detect if you want to create the intensity from phase, you use interference, and similarly, when you want to create convert intensity into the phase, still you need interference. So this principle of interference is used both in direct detection as well as in coherent detection to basically demodulate or detect the phase systems. So PSK and COM. So that's all for today, and I did not include the receiver section today because it will be, again, receiver is still, again, it will be a long session, both receiver and DSP. So we'll discuss it in the next session. Since we covered almost 1.5 hours, more than that. So, so any questions if you would like to ask, or any doubt or anything, we can use the rest of the time.
Please remind when the next session is planned.
Sorry, what did you say?
Please remind when the next session is planned.
It's the same time next Sunday.
Okay, thank you.
Okay, Abby, I think it's good. We will ask people for feedback on this presentation and also indicate who participated with the reply to this email. Okay, guys, Abby, thank you, and see you next week.
Thank you, Abby.
Thank you. Thank you very
Thank
much.
you very much.
Abby, thank you very much.
Thank you. It was very good.
Thank you. If you have any doubt or question, you can also email me. I'll be happy to reply. Thank you.
Keep safe, Abby.
Thank you. You too. Enjoy ECI. I hope I will come soon.
Yeah, the tea is waiting.
Of course, I have tea here.
Thank you, Abby.
Thank you.
Bye-bye.
Thank you. Bye-bye. Bye.